In this video, we'll take a deep dive into triplanar mapping to fully understand how it works. Each step of the way will be supported by a visual explanation so that we can see what is going on behind the scenes. Also, we'll recreate the effect in Unity by creating a triplanar mapping shader that applies texture to this rock. Finally, we'll look at how to solve one of the most common issues regarding triplanar mapping. So, let's get started. First, let's start with an overview of the most common way of texture mapping. And to understand it better, I'm going to demonstrate it on this delicious croissant. Well, it doesn't look that delicious without proper color, so let's fix that by applying this texture to it. You see, texture mapping is nothing more than assigning parts of the texture to specific parts of the model. The reason this texture looks so funky is because it was specifically created to apply perfectly onto this croissant. To support that perfect application of the texture, each vertex of the croissant contains a special two-component value that specifies where on the texture should we fetch the color. These special two-component values are called UV coordinates. Each component of the UV coordinate needs to be in the range between 0 and 1. You can think of them as percentages of the width and height of the texture. This technique of texture mapping works well when we have these specialized textures and meshes that contain UV coordinates. But this special texture can only be applied to this croissant and then nothing else. What if we have a generic texture or a mesh that doesn't have a set of predefined UV coordinates? Well, to sample the texture, we would need to calculate the UV coordinates somehow. For example, we could use the world position to calculate the UV coordinate. However, the world position is a 3-component vector, while the UV coordinate is a 2-component vector. Well, no problem. We're going to use only 2 components of the world position. Let's pick the X and Y since they're the first two and see what happens. Also, we've previously said that the UV coordinates need to be in the 0 to 1 range, so we need to somehow transform the raw position into that range. First, let's remove all negative values by using the absolute value of the world position. Then, we're only going to consider the decimal part of the value. To get the decimal part, we can use the fraction node since it removes the whole part of the number. The result is texture being applied in the direction of the world z-axis, which makes sense because we only used the x and y components of the world position. This means that changing the position along the x or y-axis will change the UV coordinates and thus offset the texture. But moving along the z-axis won't affect the UV coordinates, meaning that the applied texture will remain exactly the same. Because of that, it looks as if the texture was projected onto the surface. That's why this texture mapping technique is commonly called projection mapping. Previously, we randomly decided to only use the x and y components of the world position when calculating the UV coordinate. But we could use only the x and z components, or the y and z components of the world position. If we use the x and y components, the projection will happen along the z-axis. If we use the x and z components, the projection will happen along the y-axis. And if we use the y and z components, the projection will happen along the x-axis. That's really cool and all, but all projections produce stretching in certain areas. Why is that happening? Well, let's take a look at movement of one point across the area where the stretching occurs. We can see that its UV coordinate doesn't really change during the movement, since most of the movement happens on the axis that has been excluded from the UV calculations. That makes sense, but how can we get rid of these stretch areas? Well, what if we could use only the good parts of each projection and then combine them all together? Then, the final result should contain only the good parts without stretchings. There's only one question left. How can we determine where each projection should be visible? Well, let's examine one planar projection and its corresponding stretch area. Also, let's visualize the orientation of the surface with a vector that is perpendicular to the surface. This kind of vector is usually called a surface normal. Now, if we scale the visualization size of the surface normals based on the angle with the projection direction, we can see that the stretching increases with the increase of angle. We can use this correlation to blend the influence of projections based on their angle with the surface normal. And we're going to do that with a little bit of vector algebra. A nice feature of vectors is that they can be presented by a linear combination of 3 world axis vectors. Since the projection's directions are aligned with the world axis, we can use this information to adjust the influence of each projection based on how much each world axis affects the final vector. So, if the surface normal points in this direction, we would use more of the projection along the z-axis, while in this case, we would use more of the projection along the y-axis, but you get the point. Armed with this knowledge, let's combine these three planar projections based on the angle with the surface normal. The result is a nicely wrapped texture around the whole object with minimized areas of stretch. This kind of texture mapping technique is called the tri-planar texture mapping. And you may be thinking that the blending area is still pretty visible, but let's see how it looks with a more generic stone texture. Much less noticeable, right? Since we got a basic understanding of tri-planar texture mapping now, let's see how we can implement it in Unity to apply textures onto this rock. If you think this kind of visual approach helped you to better understand the tri-planar mapping technique, make sure to let us know by leaving a like on the video. This will give us an insight into whether we should continue with this style of visual explanations or not. Now, let's put everything we learned into practice and create a tri-planar mapping shader in Unity. I have a rock asset that contains a set of UV coordinates. Also, I have normals and roughness textures that can be applied via regular texture mapping, but I don't have a corresponding color texture that can be applied directly. So, we're going to use tri-planar mapping technique to apply the color texture to this rock. Let's start by creating a new HDRP lit shader graph and calling it something like Tri-planar mapping shader. Then, double-click on it to open it inside the shader graph window. First, add three texture 2D properties: a base map texture for the base color of the rock, a normal map for more detailed normals, and a roughness map that will control the smoothness of the surface. Before we start creating the tri-planar mapping effect for the base color, let's just quickly apply the normal and roughness maps to make the rock look a bit nicer. There's nothing special going on here, so we're just going to proceed to the good stuff. As we learned before, applying the tri-planar mapping technique is a three-step process. First, we need to calculate the UV coordinates from the world position and use them to sample the base texture 3 times. Then, we need to calculate the influences of each texture sample so that we can combine them together. Finally, we use the calculated influence to blend all 3 planar projections into the final tri-planar projection. Let's start by calculating the UV coordinates from the world position. To access the position of the fragment, use the position node and make sure the space option is set to world, since we need to use the world position to calculate the UV coordinates. However, in HDRP, the world position is relative to the camera to provide some easier shader calculations. So, if we just use this world position directly, everything would move when we move the camera, and we don't want that. To fix it, make sure to add the offset of the origin of the world space to our position. This should now provide a correct world position that is independent of the camera. Next, we need to convert the world position into 0 to 1 range by applying the absolute and fraction nodes. All that is left to do is to pick out combinations of 2-component vectors from this 3-component result. An easy way to do that is with the swizzle node. Just specify the mask to these combinations: YZ, XZ, and XY. These are now our UV coordinates. We can use them to sample the base texture 3 times. Let's see the results of each texture sample by connecting the sample to the fragment output. The result matches what we've learned previously. We get the 3 different planar projections, each along one of the world axes. We've now confirmed that the UV calculations are correct. The next step is to calculate the influences of each projection. This calculation is based on the NVIDIA presentation from 2007. I've provided the link in the description if you want to check the whole presentation, but the important part regarding tri-planar mapping is contained on this slide. It presents a way of calculating influences of planar projections based on the normal vector, by applying a little bit of bias and scale to smooth out connection areas. For clarity, we're going to implement this as a subgraph and then use it in the main shader. Right-click in the project window and select Create, shader graph, subgraph option. Name it Tri-planar projection influence. The input for this subgraph is the normal vector, while the output of the graph is a 3-component vector that represents the influence of each projection direction. All that is left to do now is to implement the logic specified in the presentation slide. Also, you can expose these hard-coded values if you want to tweak them from the material inspector by clicking on this plus sign in the Blackboard window, but we're not going to need it for the purpose of this video. Back in the main shader, we can now use this subgraph by connecting the normal from the normal map. However, normals sampled from the normal map are in the tangent space, so we need to transform them into the world space. Make sure that the type of the transform node is set to normal instead of position. Finally, we can use the output of the subgraph to scale the planar projections and blend them into the final result. Make sure to connect the correct component of the weight vector to the corresponding projection. And that's it. Let's have a look at how the rock looks now. As we can see, the result is a smooth blend between multiple projection directions, with the connecting areas barely visible. This looks really nice. There's just one small tweak that I would like to add. Depending on the size of the object, the applied texture could appear too small or too large. Let's add a tiling property for the texture so that we can control that. This is actually really easy to do. Just add a new float property called tiling and set the default value to 1. Then, add a multiply node to the world position before the absolute node and multiply the position with the tiling factor. That's all there is to it. Let's check how the tiling factor affects the result. By increasing or decreasing the tiling factor, the projected texture appears smaller or larger on the object. Awesome! We have a much greater control over the final result now. Well, this is perfect if the rock is static in our game. However, if we need to move this rock, the texture will change. This is one of the most common issues with triplanar texture mapping. Let's see how to avoid this. The trick is to swap the world position with the object space position, since the object space position will stay the same when the object moves across the scene. Also, make sure to update the normals as well. They also need to be in the object space now. With that, we get a stable result that isn't affected by the movement of the object. I just want to note here that this isn't a fix for the world position. It's just a different way of calculating the UV coordinates. Both ways have their usages in different cases. For example, when applying snow texture across multiple different objects, it would be better to use the world position since the textures will match perfectly across multiple objects. And if you want to learn how to do just that, make sure to watch this video. It explains how to use a planar mapping technique to create a snow shader that applies a snow texture across the whole scene. And that's all there is to triplanar texture mapping. Now, if you still feel like you didn't quite understand a specific part of the planar mapping process, make sure to let us know by leaving a comment down below. And that's it. Thank you for your time and good luck with your creations.